give it to you, and then you can introduce everyone, and we will put them in the spotlight. Some
Mm-hmm.
initial remark, and then we'll quickly jump into the Q&A coming from the participants. Uh, for a rough ballpark number, maybe after 30, 40 minutes, uh, we will leave those three questions as the guiding question and then depend on the participants. Is it okay?
Yeah.
Yeah, we will try that.
Great.
So, mhm.
So, hi Deepankar, is your mic working? Everything great?
Yeah, should be okay. Are you able
Yeah.
to hear me?
Yes, yes, yes,
Okay.
yes. Okay, great. So we have all the panelists. So let's start.
We can hear. Mhm.
So hi everyone. Welcome to second day phase 4 of ISHA. This is one of the major highlight of this symposium. We have 4 panelists for science session, and after this we have plenary talk. And thanks to Ankush, he has agreed to be moderator among big giants. So I will give to Ankush to take care of this session.
Yeah, thank you, Pratik. And I should say thank you for this opportunity. And it is definitely, these are big giants, and I hope I'll able to moderate properly and get something very interesting from this panel. So first of all, we have very excellent panel members here sitting. So I will just introduce one by one. We have Madhulika Guha Thakurtha, known as Lika, and most of us know most, I assume that. And she's currently a program scientist at NASA Astrophysics Science Division. Mainly, she has played a very key roles in NASA for stereo, involved in multiple missions like SDO, Valorant probe, Parker Solar probe, even Solar Orbiter. So she has immense contribution in this heliophysics and even you can say space weather. Then she has been very much known for her NASA's Living with Star initiative, and currently AI labs uses to the space physics. So welcome, Lika.
Thank you.
Then then we have second very known figure in India also, Dipankar Banerjee. He is very much known as Deepu to community and as his approachable, always approachable, and he's guided multiple number of PhD students and number of other students. So currently he's Vice Chancellor, Indian Institute of Space Science and Technology, IST, Trivandrum, where I am also currently same city. He is a co-chair of Aditya Alvan Science Working Group and even a past president, just recently, a past president of Astronomical Society of India. Also, he held a very key position as a director of ARIES, and then he came to the IST. So he's an expert of solar physics, imagery waves, solar atmospheric heating. So we'll be hearing him as time progresses. Welcome, Dipankar.
Thank you. Thank you for the opportunity.
Next, we have Dibendu Chakrabarti. He's currently professor and head of Space and Atmospheric Science Division, PRL. He's currently a PI of Aspects payload on Aditya L1, which is delivering excellent data and science. And he's also a member of Aditya L1 Science Working Group. Also, is involved in multiple other missions. Also, Venus Orbiter mission, PI for science, PI for some payload. Then Disha, which is for aeronomy mission for India. So it has a significant contribution in these missions and building payloads. His main expertise, I will say, cross-domain from solar wind, magnetosphere, ionosphere dynamics. So we have some cross-disciplinary person. Welcome, Dibendu.
Thank you, Ankush.
And then we have Yasmina. Sorry, I have to pronounce properly if I am not. Yasmina Magadhalinich,
Yes.
right?
Yes.
Okay, somehow, thank you. So, yeah, Yasmina is currently a senior researcher at Royal Observatory of Belgium, and she is having excellent experience lasts more than 15 years as a space weather forecaster, which is very key, very proper to the theme at present. She has been also involved in Euphoria heliospheric model team to build up, which we know very one of the excellent model currently available in our space physics. So her expertise from science, from solar eruptions, solar radio emissions, CME modeling, and space weather forecasting, and she will enlighten us on data specs during this panel. Welcome, Yasmin.
Thank you.
Yeah. So to set the stage, I will. We have around 40-45 minutes to talk, and then we'll go to the participation, so they can interact with the panel and answer the questions. So we'll start with the Lika. So she's already ready with Corona behind her, which we'll be talking about. So Tej,
Hey,
how
I had
sure?
to get up very early for you guys, okay?
Oh, thank you very much. I can understand. It's a very different local time. Yeah. So for a broader audience and to stay, because we have even, I think, master students sitting here, so they may not be aware about what is even space weather. So Lika, can you just enlighten us how we define actually space weather and what are the critical regions of this various layers from sun to the earth system that we really need to understand to predict it? You can share your
So,
slides and
yeah, let me, and some of this perhaps will be addressed in what I'm going to. So since we were given 10 minutes, I thought it's always good to put some words down and then elaborate. So that's what I want to do. So let's get started. And okay. And so, yeah, I mean, the question you're asking, these are all the right questions. And where we begin always becomes kind of that process, right? Because we like to see stuff individually from our vantage point. But the sun is a system, and we need to study it as a system. So when we think about the sun, we think of it as an object, a distant star we observe, and that has been how we have solar physics has evolved, right? But that is not quite right. The sun is not just an object, as I said, it is a system that extends far beyond its visible surface, which we observe through the solar wind, through magnetic fields, feeling the vacuum in space in which all the planets reside, everything. And Earth is not outside that system. So do you see kind of it's interesting? And we are embedded within it. So space weather is not something that simply traveled to us to answer your question, Ankush. It is the evolving state of the environment we already live in. And that shift from seeing the sun as an object to understanding it as a system. Because once you see the sun as a system, the questions we ask and the way we answer them begin to change. And of course, this is something that started when we started living with a star, that we actually live inside a star. So we've spent decades building extraordinary observations. Soho showed us the origin of storms, solar storms. Stereo gave us structure. SDO gives us continuity. But we do not just observe the sun. As I said, we live inside its atmosphere. And this is a very important notion. And yet we still tend to describe it in terms of events, flares, CME, storms. But the sun does not produce events. what it produces is a continuously evolving state in which we, planet Earth, is immersed. So space weather is not episodic, it is continuously evolving. So the challenge before us is again that shift from detection to understanding to prediction. That's where we are moving. And the shift requires coupling across domains, from the sun to the heliosphere, to the magnetosphere, atmosphere, and ultimately to our technologies and society. And that's the connection with space weather. The frontier is no longer about seeing more. It is understanding what we are already immersed in. The frontier is, can we turn this continuous stream of observations, data, into a system-level understanding that allows us to anticipate space weather, not just react? All of you had good questions, right? That sort of guides this panel. And this is the one on bottleneck. And if we are honest, the challenges ahead are not just scientific. I think they are structural also. Let's take fragmentation. Each mission in its own right is a masterpiece, but the sun is not segmented by instruments or funding lines, and they do not yet form a seamless system, all of these missions. Multi-scale problem. We model processes at specific scales very well, but the coupling across scales, that still remains fragile. We understand individual processes well, but struggle to connect timescales from minutes to the solar cycle. Prediction without physics grounding. We have models that correlate beautifully until they don't. We know that happens. Correlation without causation becomes brittle under stress. Then there's the operational gap. There is a distance between research-grade insight and something that can run reliably, continuously, and transparently in an operational environment, something like what NOAA needs, right? And finally, the uncomfortable one, we have not truly observed the full range of solar behavior we must be ready for. We are, in a sense, for rare events using non-extreme history, we haven't been able to train ourselves on that because we don't have the data. We are very good at explaining yesterday's storm. We are getting better and better. But the next decade demands that we become credible at anticipating tomorrow's storm. So what is changing now is not just that AI works, it is how it works. We can think of this shift, I think, in, let's say, 3 steps, like I have data to representation to reasoning. And what is representation learning? AI is no longer just extracting features, it is learning relationships across wavelength, time, and structure. Think of something like SDO. What does it give us? Then comes foundation model. These create a shared language across solar data, not one model per task, but a common representation that many problems can build on. And that's kind of important. These are not just models, they are actually built to be infrastructure. Then comes multi-vantage point observations. And we are beginning to move beyond single, lines of sight toward 3D time evolving coherence of the system, pulling data together from whichever direction we can that our missions will allow. Now, this is important. This is not about replacing physics, right? Physics provides constraint. AI provides flexibility. Together through physics, ML hybrids, we can explore ensemble futures, uncertainty as a feature, not a bug, and even because we don't do uncertainty still very well, and even rare extreme events that we may call black swan type of events. So the shift is we are moving from models that describe the sun to systems that begin to think with it. And so there is always, uncomfortable gap, truth, whatever you want to call it. Our observations have outpaced our understanding for sure. We have abundance of data, not from all the key regions, but still we have a lot of data, but not necessarily system insight. We see more, but we may understand less than we think. So the bottleneck here is no longer just measurement, it is interpretation. And what this makes possible as we start taking into account these changes, we move toward probabilistic forecasting, not single answers, but distribution of possible answer outcomes. And this is what the Earth weather site, climate site has been doing for a while. A lot to learn from them. We begin to explore rare and extreme scenarios, not just the most likely ones. We can reason across domains, connecting solar, heliospheric, and geospace processes. And most importantly, we shift our attitude, our thinking from detection to anticipation. And this doesn't change what we can do. It changes how we do science. We move from isolated studies to connected systems, okay? From single models that we are used to dealing with to shared infrastructure that, say, Surya Foundation model is providing, from answers to distribution functions, from analysis towards scientific reasoning systems. And so these are, some of my thoughts for our younger members in the community. What am I trying to say here? If I may offer some, more personal thought, the most important problems in this field do not sit within disciplines as we have traditionally studied. Solar physics, magnetospheric physics, ionospheric physics, heliospheric physics. No, they sit between them. So work at interfaces between data and physics, between solar and geospace, between research and operations. These are just examples. Build things for others that others can use. Data sets, tools, models. That is how impact will scale. Just like, when we shared observations, that resulted in a huge impact. And solar physics was a pioneer in that. And Alan Title, and I'd like to take a moment to really express gratitude for this giant of a physicist who, helped push this field forward, who passed away about 2 weeks ago. He made a demand of his community that we are going to make all observations available. And that is why we are where we are. Clarity matters more than complexity. And perhaps most importantly, learn when not to use AI. Not all problems need to be treated with AI. or cannot be treated with AI. So the judgment will distinguish basically, rigorous science from convenient answers that we produce sometimes. Because impact will not come from solving one problem. It will come from connecting many. And this is my, closing thoughts. We don't just study the sun as a system. We live inside it, and we are finally beginning to understand it well enough to anticipate it. But a lot of work to be done. Thank you very much.
Yeah,
Good
thank you,
to-
Lika, for covering all the aspects almost. So we'll just rapidly go to next panelist and then come open the floor for question answer. So second, Dipankar, can you just talk about how now see we have around 400 years observing the sun. So what are the key still we don't understand about solar flare initiation or CME, which is critical to space weather, and on your thoughts on for young generation.
Okay. Yeah. So I will answer your question. Just let me get first this clarity. Are you expecting any presentation from all the panelists
No,
or
no,
no?
no,
Okay. So
not.
that's
It's
fine.
optional. Yeah, it's
Yeah,
optional.
yeah, yeah. So I was pulling up one slide, but then anyway, I would prefer more question answer than showing more
Yeah,
slides.
that's so we want to reserve more time for question answer. Yeah,
For
that
questions,
will.
that's correct. Yeah.
Mhm.
So yeah, you're right. There are there are different kinds of variability in the sun. So one is the long-term variability, what demands long-term data, several hundred years or millennia, which is directly related to our climate, which is also very important. Why we still do not understand in the last century why this cycle 19 was so strong and others are much weaker, and whether we are getting into more weaker cycles in near future and so on. The other thing is understanding the each cycle variability, daily variability, and certain periods which is more potential to these dynamic events. Now, to me, if you understand the source, then the impacts can be understood better. So I think our limitation is still understanding the source region and complexity of the source region, because no two CMEs are the same, no two active regions are also probably the same. But then how you sort of generalize these or try to create different baskets and try to link their effects is the state of affairs. But what I my personal feeling is what is important is in our generation we were not doing it. We were only focusing on one wavelength or two wavelengths, and probably remote sensing into only again into UV or near UV. But now that is not affordable. If you really want to understand this complete coupled system, what Lika also pointed out, you need to understand remote sensing. You need to understand also in situ. If you have these two combination, then only you will be able to have a comprehensive understanding of the source and the effect, and then eventually the impact of it, whether it is geoeffectiveness or in the satellite at the different vantage points, can be only studied if you combine these two. Because you need validation. Of course, your model will do some prediction, but then the impact study demands inclusion or validation in terms of your in situ observations and the model parameters as well. So I think that's where we stand at. And I'm really fortunate that I had always very good students. Initial days only we were looking at again remote sensing, but now my more younger students are looking at the in situ aspects also. So I'm learning and I'm realizing this fact that how important it is to have a multi-wavelength, multi-vantage point, capabilities, and combination of remote sensing and in situ. So that's about the physics, understanding about these phenomena. But I will talk about the impact part of it, and what I think about the younger students should look at for their future endeavors. I will come back to it later on. So
Yeah,
for
sure.
now, to answer your this specific question, that's all from my side.
Yeah, thank you for that. So multi-point, multi-wavelength study is very critical at modern era, we understand. So we'll just hope to, Yasmina. So can you just tell us about like what are the gap areas still we have for CME evolution and propagation in interplanetary space? Because still our forecast models are not very good, right? Still we have a lot of inaccuracy. And
Yes.
what we can do to make it better.
So in principle, if I can share one of my slides.
Yeah.
So let me. Why I want to share it, because once we talk about the operational space weather, then we have to, yeah. I'll just put it like this. Probably it's good enough not to be, or maybe I can put it in the slide slide mode. So what do we need more is it's not only in the operational space weather. Oh, sorry, this is another thing.
Yasmina, at the bottom, the slide of presentation.
Yeah. Okay.
Yeah. Yeah.
Okay. So when we talk about operational space weather and when we talk about space weather in general, it all starts with observations, as Dipankar already mentioned. And I had my career path drove me from radio observations up to the multi-wavelength observations, all type of multi-wavelength observations, including the in situ measurements. And that is all what one space weather forecaster needs, or space weather scientist, because we start from the sun, and it's important to understand the processes on the sun, but also their propagation, because once the CME propagates away from the sun, it propagates in dynamically evolving solar wind, which means it's being shaped within the solar wind. And the impact which it has at the Earth, of course, it's also something which has to be seen in situ measurements and in all the geomagnetic parameters like DST or KP. So we start with observations, but then it's not possible to cover all the points and all dimensions in the observations. And this is why what I've learned when I started to work at KU Leuven, because I work also in the modeling group of CMPA, is that the modeling is a very important chain in understanding the space weather events. Why? Because modeling allows us to see the things in the 3D space. And this is a very, very important thing, because what we have in observations in situ, that's one point in the space and time. And these are the time series, and they just show really one thing, while everything we see everything which happens are the processes which are three-dimensional processes, very complex things. So this is why it's important to have also multi-spacecraft observations, which allow us to see things from the different viewing points. And at the end, these last maybe 10 of years, I have been working all the time trying to combine observations and modeling. But I've last few years with having more students and more discussions, because new brains bring always new ideas. I realized that that's not the end, that actually we need also analytics and theoretical description, because in order to understand the processes, we need to make the full circle from the observations, modeling, which help us, and analytics, understanding of the physical processes. And that is also what we need as a space weather forecasters, because space weather forecaster starts with observations, looking at the sun, looking at the possible eruptions, looking at the possible sources of the solar wind. And then it tries to do basically a model, either to model with models like we have Euphoria, or now we have in-house models, new models, Coconut and Icarus, modeled it in order to see how the disturbances will propagate towards the Earth, and then forecast the arrival of the disturbance. So trying to kind of make the final idea on what we could expect at the Earth. So that's something which is, I think, very, very important. And in principle, I can stop sharing it now, just go back to discussion. And you asked me what, as a space weather forecasting person, we need now. We need we need another LASCO or another, if you would ask me for a wish list. So we would need new SOHO, and we would need the new stereos. That's I think the L1 mission, which really follows the sun, which is stereo-like mission all the time, because once we obtain, because I started to do forecasting even before we had all the time stereo data, and once we got the stereo data, it's like you suddenly get the glasses and you see everything much more clear, because you see what happens on the backside of the sun. So why that's important? Because the sun, as it was said before, it's not a thing by itself, it's a full system. So it's not only what happens on the front side of the sun, which goes towards the Earth or some spacecraft, which is an L1 position, but it also has a global structure. The global magnetic field of the sun is extremely important, and we don't understand how the things look at the backside of the sun if we have no observations from the backside of the sun. So as a space weather forecaster, that would be my first wish list, stereotype of observations.
Yeah. Okay. Thank you, Yasmina, for wonderful insights on this. And I understand it needs synergy between observations and modeling to really attack this space weather problem. So we'll go to the next, and then we'll have further more discussions as it evolves. So Dibendu, actually we are sitting at 100 year of active sounding of ionosphere. I just noticed that we finished first sounding 100 years back of the ionosphere of the Earth. And so, what do you think where we stand now in terms of space weather and what we need to do and how youngsters can contribute?
Yeah, thank you, Atush. The way I look at it is that the space weather is a large system, and if we have to have a prediction of a space weather system, which the driver is the sun in one end, at one end, and then there is propagation of the solar wind and the solar transients and its impact on the other side of it. And eventually, it is a system of systems, not even a system, but it's actually a system of systems. Now, if we have to have a predictive capability, how we have or acquire the predictive capabilities, there can be various tools for it. Some of the tools can be AI-driven, some of the tools can be physics-based, some of the tools can be physics-informed ML. So we can look at in various ways in this system to have the ultimate capability, because our eventual goal is to understand that how the variability of the nearest star is going to affect our immediate environment. Now, if you look at if you treat it as a system of systems, in every field, let us say sun or the solar wind or interplanetary propagation or magnetosphere, ionosphere, thermosphere, if you look at it, I see there are four domains, four ages that can be defined. And initially, it started with discovery period, where a certain time period can be attached to. Initially, people started every good result was a discovery. There in every such domain, whether it is sun or whether it is heliosphere, whether it is magnetosphere, ionosphere. So initial periods, and nowadays also the discoveries are happening, but then in terms of regions, identifying different layers of the sun, identifying the gross properties of the interplanetary medium, the different layers of the magnetosphere or different parts of the ionosphere. All these happen during the initial years, maybe 15, 20, 25 years. You can define it and we can fine tune those time scales. Then came the dynamics part of it. The discovery of the dynamics. So at each such layers, people started focusing on the dynamics part of each, whether it is sun or again IP medium or magnetosphere or ionosphere. And the third domain, that third time scale, that time period that I see is a coarse system science. I mean, in the sense that we understand in a coarse manner, because our tools were not so refined at that point of time, our spatial and temporal resolution were not so good. It was okay, but it was just at the initial years of these explorations. So what we did is there was a realization that it's a system probably, and then we started exploring this. It's a core system science. And then in the last maybe 20 years or so, we have started focusing on micro scales. I mean, looking at processes which are happening at a very small scale. For example, reconnection, magnetic reconnection, which is happening at an electron gyro scale. MMS, for example, in the magnetospheric mission, we focused on that. Now, what is missing in this is actually, and we had a deliberation on this at different forum, is a mesoscale understanding of each of these systems, because mesoscales, through mesoscales, the energy and other information, it is actually a messenger or a connector scale, which transports the energy and information from the smaller scale to the larger scale and vice versa. I can give you a particular example of that, and why it is important is because if you look at any such system and try to see how many scales you can define, there is a very good paper on that by Daniel Verskeren on this. Even if you look at the solar wind, there are 13 solar wind, there are 13 scales you can define both in spatial and temporal domain. So therefore, once we try to propagate the solar disturbances which are driver to right to the ionosphere or on the Earth, you have to deal with 13 scales, which are some of them are spatial, some of them are temporal. I mean, both spatial 13 scale and temporal 13 scales. It's difficult when what it does is it makes it a complex system, because at the intersection of two different plasma domains, the way they connect with each other, that becomes that much more complex, because you are talking about then 13 scales both in spatial and temporal domain. And you can define those scales. For example, gyro radius, you can take it as a spatial scale gyro. Period, you can take it as a temporal scale. Now, what it causes problems is that you are now talking of a system of systems where we know and understand certain systems, all the systems in a certain way. We have addressed different part of the system, but what happens that when this system of systems or when these systems get combined, then there are emergent behavior. What I mean by that is a non-obvious side effect of bringing together a multiple complex system into a bigger framework. This is the problem I feel in the space weather prediction science as of today, in my understanding. Why it is? Because if we are not able to transport, let us say, a solar wind under normal circumstances, or maybe CME, or in the interplanetary medium, a stream interaction region, if we are not able to transport it and make it arrive at the Earth and then, or maybe any other planet, and evaluate the impact of it, it essentially points towards that certain part of it you can model it very well. Even with AI, there can be emergent behavior which you will not be able to predict, because it's a problem of complex systems coming together and giving rise to emergent behavior. So therefore, there has to be, as Lika pointed out, that there has to be an approach which is not only AI-driven or ML-driven, but also physics-informed AI or ML and other physics-based models also have to come into picture, because we have to understand each of those systems' behavior in a certain way, so that those insights can get into the predictive capability as well. So this has to go parallelly. Once is the predictive models, and then the understanding has to go into those predictive models so that we can understand the emergent behaviors. Because if we have a storm, which is once in a century, and if our predictive models are not able to predict it, let us say, at that point for that storm, it may be doing all right for 10 storms, but then if it is not able to predict the occurrence right from the sun to the impact, then we are not there. I mean, then those models actually fall flat. So that is one thing we have to keep in mind. In terms of, so outliers will be a problem in terms of predictive capability. And because of those outliers, I think systemic understanding is very important. Now, because of in this panel discussion, I can focus on specific problems which has been highlighted in the requirement. I can do that, but I think that can come in the discussion. But my point here is that we require and reiterating what earlier speakers have said, that from the driver to the impact, we are talking about a system of systems which are inherently complex in nature, and interfacing those systems, particularly at the conjunction of those systems, are very, very critical for us to make a prediction capability in the longer run. So AI may not solve, as I completely agree with Lika, that AI may not solve all the problems. We may have to have multiple approach. And unless we understand or put those insights into those ML models or forecasting models, maybe we will still have to live with the outliers in the long run unless we address those problems. So there are specific problems. I'm not getting in there in each domain, but for one specific example, I can give that we still don't have a very good model to, let's say, the CME propagation and the uncertainty in the time, arrival time, when it reaches to the Earth. From the sun, it is getting launched, and we have not eliminated those uncertainties. So once one of the principal drivers, their arrival on the Earth orbit, is not predicted so well, we are definitely a lot of distances away from that particular goal. So multi-point observation. Ideally, there can be cluster of satellites or constellation of satellite at multiple places to address the scales and spatial to delineate the spatio-temporal scales. That is the ultimate approach, but then it's expensive. So I think people have to put their hands together. International cooperation has to come in picture. And for science, I think that is the goal that we should all work with.
Yeah, thank you, Dibendu, putting complexity of the system, and really we need multi-point observations and multiple approaches, AI, physics-based, and data-driven models. That is a critical. So there, I think we can now open this for question answer, because I do have some questions to navigate, but better to let's go to the participants and then let's go ahead from there. So there are some questions. Maybe Chitrit, what should we do? Directly they can ask, or should I just read it?
If they want, they can ask it by themselves, or you can also read them.
Yeah, that is good. Maybe if they can ask. Maybe. So Ashwin Amrita Raj, you have some questions. Okay, can you unmute and quickly ask? So try to be precise question. So
Yep.
that will help.
Yep. Thank you so much for the wonderful discussion and everything. So I'm working on CME velocity prediction, and I found that the solar cycle 24 behaves well, whereas in solar cycle 25 the correlation shatters for me. And I felt like I heard that Surya model have a similar kind of issue where the prediction model doesn't work well for solar cycle 25. So I just want to hear the thoughts from Lika on what might be the reason behind the problem in prediction of solar cycle 25. Yeah, we understand
It is the data we train on. So, that it clearly reflects some of that behavior. But the complexity in these very large foundation models goes far beyond that. And so what we have to do, and we are working on creating the second version, and we have to figure out, what is going to be in our training data set. And so we will actually have a workshop sometime in fall, where now we will integrate the community. The first one was done based on a core team going after, like, this is the time scale. We can't choose, every 12 seconds, right? It's still not quite possible. So we chose every 12 minutes. We chose continuous data for a certain number of years. And so now we are going to ask the questions, we're hoping that there'll be a lot more sort of applications done to sort out which kind of data selection might lead to different kind of application. So I don't think we have the luxury of thinking any one thing as being the benchmark. The benchmarks have to be tested continuously. So that's where we are. And some of the issues with cycle 24, I think, are and understood. I could give details. The engineers and the scientists who are directly working on it, because this is actual work in progress. But this is how it is going to move forward. What I want to say, taking this opportunity to bring up the foundation, Surya Foundation model, as one of the first ones in our field, is that, I heard a lot about modeling, and utilizing this capability is very much like this. So when I started Living with a Star science part of the Living with a Star, there was a concept I invoked, which was called strategic capability. That kind of really gave rise to the coupling of models that we are calling system science today, right? From sun to solar wind to magnetosphere, ionosphere, etc. And we could be looking at a foundation model and create, because we have sparse data, sun is the only thing where we have pretty good data. But then you come into the corona, which is where most of the effects we study, the sample becomes very sparse. So we could begin to form foundation models of different region that we understand either with data or data with physics informed knowledge from the models we have done, right? And then start beginning to couple them. And this is a very naive notion, because till you have done it, you don't know all the issues. But, with everything that is going on, we can begin to imagine then coupling this together. And
Can I comment?
Yes, and I have one more thought. So my thought right now for community is that single model approaches give us just that single viewpoint insight, not the actuality. And that's why often, they don't work very well in all circumstances. So moving away from single model to actually capturing the probabilistic output is very important, and quantifying uncertainty. Thank you.
Yeah. Yasmina, you had comments?
If I can comment, I think I have a little bit more concrete thing about that. Is that in principle, when you are looking at the CME propagation, CME strongly interacts with the solar wind. We did that with my students and through the modeling and observations, which means that in every solar cycle, the CME propagation will strongly also depend on the shape of the solar wind. And during last two solar cycles, the solar wind is not too bimodal. So the point is that what do I mean by that? If you look at the distribution of the solar wind through the whole solar cycle, you will find that the contribution of the fast solar wind is much smaller, so that the distribution is asymmetric. But where you expect like a bump in the wind distribution of the fast wind, you don't have it. And when you now think that your CMEs propagate in the inherently slower wind, then the arrival times which you estimate will be also different than within the different solar cycle where you have more fast wind, because your CME, you know that by the drag-based model, that if your CME is faster than the solar wind, so the solar wind will slow it down. But if your CME is slower than the fast wind, then it will be pushed forward and it will arrive faster. So that kind of a role of interaction and the dependence on the solar cycle strongly influences the prediction of the, especially simple model predictions of the CME arrival.
Thank you, Yasin. Oh, Dibendu. Okay, you can go ahead.
Yeah, I just
Yeah.
want to add what Jasmine
Go ahead.
just commented. It's fully agree with that. And one more point is that not only the CME solar wind interaction, but the outlier event that I was talking about. For example, you can take the May 2024 event where multiple CMEs interacted with each other. That can happen even with stream interaction region as well. So those events to gauge the predictivity at 1 AU becomes that much more difficult. So that is one area where we need a lot of attention at present, because to gauge the geo effectiveness of those kind of events, first of all, starting from the sun, what kind of eruption probability or flaring occurrences we should anticipate, and then eventually what kind of impact that we guess or gauge at 1 AU. These are questions that require a lot of attention because these are important for us.
Yeah,
Ankush, if I may add just few more statements.
yeah, please.
Like I mentioned, no two CMEs are same, no two active regions are same, no two solar cycles are also the same. So if things would have been so easy, then the solar cycle prediction would have been also more correct. You know how much distribution of the solar cycle in terms of the strength, in terms of the timing. So what it affects, actually, what Jasmina was also mentioning, it is the global magnetic field, which is also really dictating the solar wind pattern also. So where the CME is coming from, and then as it comes out, the interplanetary field structure is again governed by the global magnetic field. That is again dictating the solar wind pattern. I mean, the distribution of the fast and the slow wind and so on. So unless the prediction models, I mean, the space weather prediction models include these elements, just based on few 12, 13 parameters, it is not going to function. It will work for some statement, and I think Dinesh also made, even if you want to train it, you have to train it with multiple solar cycles also. You just train the thing with the solar cycle 24 alone, you don't expect that will work for your 25. So if you would have trained the data with maybe 10 solar cycle overall behavior, maybe the machine will be intelligent enough to predict it better. So I think there are many elements which has to be somehow captured. And if you really want real-time thing, even observational data has to be in real time. Otherwise, our physical understanding. So Jasmina, in that sense, I had this problem with, even if you have stereo, unless you get the stereo data, in in near real time, it is not going to really help in space weather, forecasting. It will help in our understanding, but forecasting will demand the data availability in really near real time. So that is again a very important.
When we
I
had it almost near real time, I mean, a couple of hours, it's sufficient to understand if your source region of the CME is backside or a front side of the sun. That's enough already. So
I want to take another
general
turn
user, I
to
do not know
this.
whether they were getting it near real time, because the really this space weather modelers are sort of prediction centers. I don't think they were ever used stereos near real time data.
no, they
we were
Lika.
providing beacon data,
Yeah,
yes.
Lika has something, yeah.
For stereo, but I'm going to take a different tact to this, actually, because I think, to understand the sun at its very root, holistically. I mean, we still are not tackling interior very well, but let's talk about the outside. There's just so much physics we don't understand when you do CME models starting at the corona. That's flawed. Chromosphere harbors the energy. So our approaches, we have carried on for a long time. We have tested them. We are doing the best we can. But if the goal is to really go after what we need to do and what are the important questions, let's work with what we have. We have a lot, and we are not utilizing our data, for sure. If you look at the weather world, and so there's two differences between the weather world, the climate world, and ours, that the physics, the equations in the climate world is bounded. We know them, okay? For us, that's not the case. So think of what we observe and think of what we have to pull out from those observations. There's that fundamental difference. But even with that, if we begin with the assimilative approaches, taking in all our models, say, of a given region and produce some probabilistic output, we are going to see something there. So we really have a lot of work ahead of us. Yes, we can say this mission or that mission will give us more information, but we have had them. What we are doing, I mean, we're not doing true prediction. If I can say, what we do is post-diction. After the fact, one model at a time. We are not at all very good at explaining the future, but very good at explaining yesterday's storm, but one at a time. One at a time. So, we have to move from empirical forecasting to physics-based plus probabilistic prediction. Yes, the one model kind of approach has to join hands with other models to determine the actual uncertainty phase space.
Yeah, I agree. Still, we have a lot to learn physics part and model it. Yeah. So I will go to the maybe this is a nice conversation where we stand at present. Another question by Seket Muzumdar. He has for Dibendu one question. I think you can unmute and ask.
Yeah. So thank you to all the panelists for this insightful session. So I am Saikat and I am coming from the industry background. I am working on space weather analysis pertaining to satellite operations. So my question, actually, I posted all of my questions on chat. So if I were to summarize, I think Lika talked about how there is a big gap between research models and operational applications, right? And that is what I think I have personally experienced while dealing with NOAA, where they were actively looking for people to validate their research models for transition into operations. So this is an open question. Essentially, I would like to understand how do you think this gap and the bridge, that gap that currently exists between the research community and the operational community can be bridged to improve, model development tailored towards operational use case?
If I can answer straight away to
Yeah,
that.
please.
So I'm working half time at the Royal Observatory of Belgium and half time where I'm also space weather forecaster and half time at the University in Leuven, KU Leuven, where we do the modeling in the modeling basically group. So we do actually all the time, and all of my students work with some of the models, and we are trying to validate them. And as soon as we have at least partial validation, at least no more stably model, we are using them in the forecasting, in the operational services like this. We do the daily runs of the solar wind model by Euphoria. We do the CME modeling with Euphoria. And this Euphoria was validated within the framework of my project 10 years ago. So which was so we do try, and we do work on that, but it's not a straightforward and not an easy process, because the point is that often the modelers keep the model like their own baby, and then they don't really, you even sometimes like a black box, you don't even know what they tweak and how they do the things. And as it was said before, the point is that there is an event analysis. Okay, oh, it worked well with this event. I tweaked my model. I modeled well this, but that's not the point. Operational forecasting doesn't work like that. You cannot tweak your parameters. You have to put what you have there, and you have to have model giving you some kind of a range of results. So we are trying to do that, but it's not something which can be very fast done. It's not, I mean, it's a process for every single model. And then also during the AGU 2 years ago, I said that it's not good that every second person wants to have his own model because it will have its own name and it will have fulfill his own desires. So models have to come together to work on the similar or the same models and make the models better, because making like 10 models which have a slightly different background, slightly different things, and then validate all of these 10 models, this is impossible. So we need to be more coherent in what we do. So more focused to have good models and not just like to say, okay, it kind of works for my one case or my two cases. So focus to have more better models, but less of them, and to have them well validated then.
Yeah, that is a very important point. We need some global effort to have a very good model development instead of having 100 models and nearby doing same.
Now, we also
Yes.
have to keep in mind, Ankush, in this regard, that when you talk about space weather commercial prediction, it's something of a different domain, in the sense that we need to purchase many times these products. Okay. So what it essentially means that even if you have data, and I mean, you need to have your data, first of all, and then you need to have your framework. And with increasing space weather situational awareness requirement, I think that is getting into a space where it may not be free in the longer run. And so what I essentially foresee a problem is that it should not compartmentalize the whole world. I mean, that is a possibility because there is a business potential in it as well.
Yes. Agree. That is the truth. Anybody want to comment further on this, or we can move to next question?
Well, it's a tough problem, right? I mean, as I said, we started with strategic capability in living with a star, and it has worked for a while, but we kind of stopped really the quantification, the uncertainty prediction, the model benchmarking. We have none of that in our field. And then what do it doesn't matter who uses for what. If you haven't done that, then, what faith could we have in such output?
Yeah, that's a question.
So that is so important in our field, but it is still not happening at a rate that it should. I mean, I feel that we have been training everything, and our knowledge of the system has been pretty much training on quiet sun, because that works very well. And the moment something else happens, that's when everything falls apart. But we derive pleasure from showing that it matched during that quasi-quiet period. So it's a mental shift, and we have to keep pushing at it. But how do we push? Do agencies push? Or do researchers push themselves? I mean, this is a longer dialogue. If we want to make progress, and we have a lot of resources we have built, how do we put it on steroids and push? It's your generation that will figure it out.
Yeah, question to the new generation to solve.
Okay. Bush, can I add one thing into this?
Yeah. Go ahead.
Yeah. Thanks. So since everyone is talking about the space weather forecasting, I couldn't stop myself from raising this point that we have a very good example of terrestrial weather forecasting, which is much older than our community. And they are doing it on a regular basis, and we are using it as a final product. Since it was an old community, they were having good accuracy. But if you look at the GraphCast model, which is recently developed by the DeepMind, it has brought breakthrough in accuracy and speed. It's AI-based model with a 30-year, 20-year-old physics-based driven modeling, forecasting, everything was there. So my point is that AI, if we talk about forecasting, machine learning, data-driven methods for this super complicated, complex systems is a very good option. If we talk about physics-based understanding, modeling, then yes, those traditional methods will hold.
Yeah.
I may be
For
wrong. Yeah,
operational,
just my.
I agree.
Now, Pratik,
operational,
yeah,
it's good.
the point is, training. We are not matured enough or have not long enough, doing this. So the weather forecasting has gone into that. You have to see what are the number of decades they have been doing, because their model improved when they had many more data points observationally also, and also very fine data points. Our is still coarse. We know what is happening near sun, somewhere in between, and then at some distance at Lagrange, and then we are expecting near the planet what it will happen. We have so much of gap. So that means it is a sort of extrapolation, interpolation that of course machine can do it better, but for that you have to feed it with many more cases, and that's why the multiple vantage locations will be important. Multiple location will be also important. It's just not in the same ecliptic as well. You have to go out of ecliptic also. So all these has to be fed, I think. Unless we are feeding all that into the machine, I don't think the accuracies will be improved. So, but I agree with you that machine eventually will dictate, and it has to, because it needs a timely delivery also. We can't otherwise do it. Physics-based model will not deliver it in that speed.
Yeah. Practical purpose, that's better to do.
Yeah.
Yeah. So I think I will go
Can
to
I
next
just
question. Oh, okay. You want to comment
Yes,
something?
I
Sure.
want to comment. So I have two PhD students which work on the application of AI in the space weather, and I wanted to just to comment on the recent results which we had, and also on what Dipankar said, because the usual weather forecasting, they have much more knowledge on the processes which are happening. So because they have more observations, which means that all the AI forecasts which are made for the Earth space weather is much better confined. If we want to do AI studies and the AI predictions on the sun, that's much more complex. For example, what is generally often being used, a simple example, is that when you train your model, we did some studies on the forecasting of flares using the AI. When you train your model, majority of people uses in order to augment the data sets, they distort the magnetic field patches which they use. And my PhD student recently made a study which showed that basically you are not allowed to do that, because then you cannot really, your AI efficiency of predicting the flares drops for 60%, not drops on the 60%, but drops for 60%, which means we have to understand that the physics which we look into is very different if we just distort the magnetic field within the box which we take. So this is not something which is allowed to be done by AI.
So again, if you are pulling out a section of a system and trying to model that, you are going to get that. And as I said in my slides, where to use AI and where not to use AI is a judgment, and people should know that. And doing the kind of AI applications we do in a large part in the community is something everyone should look at and figure out, whether we can do that or not. I'll tell you something that I have been surprised by the Surya Foundation model and what it is doing, because it was fed, I don't know, about 8-9 years of SDO data. Not the 12-minute cadence, but the 12-second cadence, but the 12-minute cadence at 4K by 4K resolution, 8-9 filters. We are actually able to see some kind of evolution of active region. And of course, these are things being absolutely validated and benchmarked. So, it's not a result that you just, the first blush results you show, but you have to work hard to make sure what you are seeing is correct. And that, what I just told you, that was just absolutely stunning, that AI alone is able to pull from this data because there is information contained in that. It's physics that has produced the wavelength and the evolution that we see. It's able to pull out some of that information. So it's not a question of right or wrong. We have to absolutely be diligent in our application of AI to the system and ask the question, is it the right data we are using for the right questions, small or big? Very, very, it's absolutely fundamental. But I don't think we can also make progress without AI anymore, because we can't handle the amount of data we have, and we need to. We have already taken these observations in order to, understand our system.
Yeah. So I
So
would
we have a lot of
excellent, but
work.
use it with care. Excellent, but use it with care. Yeah.
Yeah. So, okay, I think we'll go on next question, maybe some different direction discussion. Sneha Pandit, is she there? Can you unmute and us in a short
Yes,
format, your question?
yes.
Yeah.
So I'm a postdoc in India, and I work with Parker Solar Probe data, like learning about switchbacks. And before this, I was working on chromosphere. So this is a very broad question, and for everybody, that we discuss a lot, that we have a lot of data, but very less science-ready data. And in the process of making the available data science ready and comparing it with, if it is simulated data, comparing it with other simulations, possible observations, and vice versa for observational data, synthetic data, and so on. The amount of effort we put and the dent we make in the sphere of understanding is a bit disproportionate. On the other hand, when we are looking at similar, like applying this skill sets to understanding questions in stellar physics, in stellar wind, stellar activity, or exoplanet detection, exoplanet atmospheric characterization, and so on, it's more or less the same skill set. But since there is way less understanding than in the heliospheric science. So my question is to make at least our field open enough, because we cannot talk about them, but making our field open enough to make it accessible for us to learn in that field and for them to learn in our field, and communicating using similar languages, using these tools, these models, these observations for understanding those questions and vice versa. This will aid exchanges and potential collaborations, and also leading to different kind of career jumps. So how difficult, and policy making wise, and also even if we decide a few people and then penetrating these two different institutes, different levels, how do you think this can happen, and do you think there is a merit in this kind of thinking?
Should I go ahead with some response?
Yeah.
Yeah, you really pointed out the right thing. Essentially, the solar physicist traditionally has this problem of isolation. We have been working in isolation, but things have changed somewhat, I would say, because you will see, in our generation onwards, we try to learn from other, whether it is extra astronomer or, as you said, exoplanet, because, I mean, the specialist in the solar community has gone into the exoplanet detection thing. The top people in exoplanet detection are all old solar physicists. So those who have done that has actually immensely really contributed to the global scenario. Your generation, as I was also trying to point out, that multi-wavelength, your skill set, how to apply in other other avenues also, you have to really master it. In fact, I only wanted to show one slide, but I know you are all familiar with that slide, which just shows the impact of space weather in so many domains, whether it is aircraft, whether it is International Space Station or GPS, or so you have possibility of working in so many environments. You won't believe it. Right now, since I'm getting more connected with ISRO program, whole day I was at the ground operation. There is an international conference going on in Bangalore. People are talking about, mostly space weather and also, space situational awareness. So all solar students can actually significantly contribute. In fact, in this group of people, Shoykot is one guy who did some master's thing. He's a physics student, but now he's working in Digantara, which is one of the leading startup company now for space weather and space situational awareness. So mastering your skill set and that application in many different, whether it is astronomy or in industry, you have to really, really, be very careful about. You have heavy demand, I can tell you, in everywhere. Uh, in general, astronomy students, because of the ability of doing lots of image processing, now everybody knows, Python coding adequately well, and also, AI. So these are the areas required for the industry. And now, since space weather is really, really getting connected with many, many space, industry applications, uh, you should actually project yourself. You should sell yourself as just not a switchback specialist, but but you focus on your skill set in what domain you have and all. So this is like the generic statement I'm making, but I thought, since you posed this question, to learn from each other and expanding and the scope, I thought I will make these comments. Yeah.
Yeah,
Sorry,
thank you.
my response was a little
Thank
long.
you. Yeah, no problem. So I think we are running out of time now. So maybe we'll not able to take other questions, but please feel free to contact panelists also. You can write a list easily and get their views. So for closing, what think, if you can give everybody last wording, maybe two-liners. Suppose somebody is starting in a space science as a young PhD students now, what advice you would like to do as a senior space physicist in this field? What they should do? Maybe start with Lika and then we go.
Make yourself, I talked about single model. It's not just that. This generation sits at a very different interface. There is no one discipline. It's multidiscipline. You have to make yourself familiar in everything. You think astrobiology is not connected to space weather? It is. Think of radiation. I don't think we can do exploration without heliophysics. And so you need to really educate yourself. Maybe you choose a fundamental focus, but your knowledge has to be deep and broad. And AI is that you will have to use away from it. And I think most of you are probably very familiar with it. But where not to use AI is just as important. If you know the physics of a system, apply physics, not AI. And I see people sometimes make that mistake. AI becomes really important when you have vast amount of data. That's when you get to some level of clarity. And now we are, of course, experimenting with, physics-informed ML approaches. And that's where I think we will get a lot, because for a lot of our community, there isn't enough data to sink into, right? So if we can connect where we have data to physics-informed area, we are going to make progress. So yes, not one discipline, multidiscipline, make it vast, and it has application globally, economically, and it's not just the traditional space weather favorites, just many, many, many more. We haven't even thought about it. Start thinking about it. See where the connections are. I think it's an amazing time in that sense because there's potential for new ideas to emerge. And I think Dibendu, you use the word emergent. That is the word. I think the basic physics, and I'm not talking solar physics, basic physics is something we have understood now for a while. But what we haven't understood are these interaction of various different kinds of physics in different domains, which also give rise to this new emergent behavior. And I think we are part of that domain. Thank you so much for
Thank you,
this
Lika. Thank you for
opportunity.
valuable advice. Yeah. So, Yasmina, would you like to just give finishing two lines advice for youngsters?
Yeah, 2 lines. Yes, it's similar like Madoglika. So know your expertise well. This is always what I say to my students. Know what you are very good in, but have a broad knowledge about everything else. So make yourself expert in data and in the coding, and get at least some AI knowledge if you can. But don't try to be a very narrow mind and have only one thing. So in one thing you have to be the best, but in the broad things, you have to have a good knowledge about everything, because first you need to know that as a scientist maybe you will need to change the field back and forth, who knows where. That's the first thing. And the second thing, knowing only one small puzzle doesn't give you the full picture. So you have to know where your puzzle has to sit in. So that helps you as a scientist, but it also help you in the career further on, because you might need to shift. We need to be, especially you young guys, need to be flexible with the working places and the moving and all these technical things. So make yourself important in many fields as much as you can. So, yeah.
Thank you. Yeah, Dibendu?
What Jasmine said sums it up. So I have nothing to add here, but only thing is that today we didn't go beyond solar wind. We have gone towards the sun, but we have not come towards magnetosphere and ionosphere. And I just wanted to point out that this is also an equally uncertain domain where the impact, this is what affects the geo and LEO operations, if I have to put it in the operational framework. So we have not understood it yet the way we should. And so this is the only thing that I want to add, that shows the complexity of the system, because it consists of many, many systems. It's a system of systems, that's why. So I think with the newcomers, like the new young blood in this field, I think we'll be able to make progress in the shorter period of time. Let's see, with technology at hand. Yeah, thank you.
Yeah, thank you. So there is a plenty of room in ionosphere, magnetosphere also. Thanks. And last, maybe Dipankar, you can sum it up. Last.
Keep your eyes and ears open. Attend more seminars in your institution, which I don't see many people doing. Because as you, just to echo what my other colleagues said, that to have this multidisciplinary approach, you need to really hear and, because we don't read that much these days, at least, but at least, listen to what is going around. And I think machine need to be, can be intelligent with your, intelligence, not artificial, but your skill set can make the machines work better. So AI is inevitable. I don't think there is any way we have to worry about it. And we should not be too negative about it also. So my opinion is how to make the machine work better. The specialists have still a lot of room. You will not lose jobs. You will be required to make that machine, make better prediction. So for that reason, I think, your skill set is still very, very important, but you should know what the machine is doing now. so that you can improve it.
Ankush, may I add,
Yes.
because I can't let Dibyendu's comments go unanswered.
Okay. Yeah.
Really, I mean, the impact of the sun in the form of space weather is really felt in the ionosphere and ionosphere magnetosphere coupling, everything else. So that's where the rubber hits the road. And I think when I have talked of system, I didn't disconnect any of this. But you kind of have to propagate from where it starts and down the chain. And when we get to the ITM region, of course, there's propagation from below that influence it too. But the primary driver still is the sun. And one thing that really surprises me when I look at ionospheric model, that the energy input that makes the ionosphere is still F10.7 and some other proxies. Whereas it's a very narrow band of EUV that we have collected from SDO, that's not utilized. And so fundamental, right? These are the disconnects. And you sort that out, your models improve dramatically just with AI/ML. So this is a connected system, and the foundation model with Surya, what we are trying to do is really apply some of these tools to the downstream applications, be it solar wind or be it in the ionosphere, magnetosphere, wherever we think this particular component influences that environment. So you are absolutely right. And I think solar physics doesn't stand alone, neither should it stand alone. It is a connected system.
Yeah. Thank you, Lika, for wonderful summing up. Everything is connected, and we really need to do all the domain knowledge is integrate and try to address this weather. Thank you very much for your valuable time and excellent panel discussion. I hope many people enjoyed it and learned a lot of things. And I look forward to meeting you later. Thank you. Bye bye.
Thank you. Thank you. Bye.
Thank you, everyone. And thank you, especially Lika, for joining us. I
Yeah,
knew
for
she
sure.
has,
Thanks.
she has to go for doctor's appointment. Yeah. Thanks
Oh,
for,
okay.
sticking this long.
Yeah, sorry for delaying you.
Yeah. And thank you, Dipankar. Thank you, Devendu. And thank you, Yasmina. It was
Yeah.
very lovely session. Yeah.
Thank you for
Thanks to
inviting.
Ankush as well. Thank you. Thank you,
Yes.
everyone.
Yes. Okay, so the next session will just start. I don't know if the participants know this or not. So Enrico has already joined. Enrico,
Yeah, can you hear me?
there? Yes, I can hear you. I think we have perfect stage to for this talk now. We have been talking about operational forecasting, AI, and now we have AI expert. So, so maybe if you want, you can just quickly check the whether you can share the slides, and
Yeah.
then I will briefly introduce you, and we'll be set.
Do you see the slides?
Yes. Yes.
Let me just check. Do they move?
Yeah.
Scrolling. Okay. Good.
Yeah. So, hi everyone. Let's start the last session of day 2 of ISHA. Very delighted to have Dr. Enrico Camporial and on this talk on machine learning in space weather. He will be covering the recent progress and future challenge. Please free to put your comments or questions in the chat or raise hand. This will be 1 hour session, mainly focused on AI, but also discussion oriented. So Dr. Enrico Camporial is based in Queen Mary, and he also has affiliation of University of Colorado. He is widely considered as one of the global experts in the use of machine learning in space weather forecasting. We have been using the operational term, and there is a model Live DST, which was developed by him and his team, which is running 24/7, which predicts DST. He has several papers and chapters and books on the use of machine learning. So very happy to have you, Enrico. Maybe you can start.
Yeah, thanks, Pratik, for the introduction. I just realized somebody asked me to send a bio, which I forgot to do, but I think you cover it well. We know each other well enough that you can do a quick bio. So thanks for the kind introduction and for the opportunity to share some of my work and my group. So this is it's a long talk, kind of a seminar, very much biased, obviously, on my own view of what machine learning is going to do and has been done already for space weather. As you mentioned, it's a perfect segue to the interesting discussion panel we just had, where obviously machine learning and space weather as they come up frequently as topics. So let me just jump into it. So for somebody like me that has been doing machine learning in general for space plasma physics, but more specifically for space weather in the last about 10 years, I realized that we all live in strange times. But yeah, being at this intersection of machine learning and space physics is interesting, but challenging for a number of reasons. So one reason why we're living in strange times is just looking at those numbers. I guess we're all familiar with the surge of AI and machine learning in general, and now in the last few years in physics as well. So if you look at the right-hand side plot, this is if you just search on an ADS database, the keywords machine learning in physics, it literally went, this covers about 20 years, I guess, from 1,000, or let's say from 0 to 30,000 papers. Those are only the refereed papers that came out in these being like 2-year bins. I am myself very much, I'm going to cover a little bit of self-advertising later on, but I'm very much involved with AGU, the American Geophysical Union. And then if you do the same exercise, looking at the keyword that, for instance, at the AGU annual meeting, if you look at the abstracts that contain the word machine learning, this has been increasing, or in this plot in particular, this is the average number of papers per month that include the word machine learning. Now, this is all good. There's a downside to it, is that if you look at the archive, I don't know how many of you still use archive as a source of information. Archive is this open access preprint database, which is divided in scientific category. If you look at machine learning, it's literally exploding. So this is just, you can guess from the slide, this is a slide I used already in the past, around October 2025, but I haven't checked recently, but I believe the numbers are the same. So the total number of manuscripts or preprint of papers put in a week, or effectively in a 5 days window, it's around 1,500, 1,600. Now, there's no possibility that any human being can keep track of this large number of papers. There's no way that out of this large number of papers, there are many that are actually significant or breakthrough. So we are inundated with too many papers, fairly low quality, I would say. Obviously, there are some hidden gems which are harder and harder to catch in this sea of papers. But this is the true state of obviously a little bit of hype versus the reality of machine learning being a groundbreaking technology. Now, as I said, let me start again from the beginning. Being somebody doing machine learning and space physics, now the sort of dichotomy we're living in is that if we look at this, do the same exercise for the space physics papers, the number is extremely low, right? So it's almost depressing in a sense. So it's about maybe 10 papers per week, which might be a sign of being still a healthy community, because we only publish like the good stuff. But to me, it's more of a sign that the community really needs to converge to more modern ways and tools of doing things. So I believe, like it was mentioned already in the panel before, it's inevitable that physics and space physics will use extensively machine learning tools. Now, I'm not going to go into, obviously, the caveats that there are good ways and bad ways of using machine learning, but I hope that the community in time will learn how to make the best use of it. Okay, so this idea that data science is the fourth pillar of the scientific method is not new. I guess at this point is something that majority of the people are familiar with. I believe it's an idea which is hard to credit, but possibly the first time this came out as a book, in fact, was in 2009. I think Jim Gray is credited with this idea, and it's, I mean, at this point, I guess it's pretty obvious, but just let me put it out on the table, is the fact that science has moved through, over the centuries, through a number of paradigms, going from being a completely empirical science, just looking at observation and try to describe natural phenomena. Then at some point, about possibly 200 years ago, 300 years ago, we moved into theoretical, using the language of mathematics, essentially, to describe phenomena. Then about 50, 60 years ago, we moved into the era of computational physics, so be able to simulate complex phenomena. And now it's almost like closing the circle and going back to the origin of what science is, trying to extract information from the data, so using data-driven discovery. Now, I'm, as I said, I mean, I don't claim to take any credit for this idea. Has been out for about 20 years now. Something that it's a bit of a self-referencing here is that myself and a number of other people about 2 years ago decided to create a new journal inside the JGR, Journal of Geophysical Research family by AGU, which is called JGR Machine Learning and Computation. And when we did that, we did sort of a statement or a vision, as we like to call it, for the journal, and in a sense, sort of a roadmap for the way we see science moving. And this is very much aligned with this idea that a novel foundational component has been incorporated into the very process of scientific discovery. And I think that's really the thing to emphasize, is not just a tool. It is a tool, but it's not just a tool to make predictions or to make things computation faster and so on. It really, the promise is really that it is a tool to aid truly scientific discovery. Now, something that I'm very proud of, it's a bit of a joke actually, but that in that same piece, this is like a 2 or 3 pages short paper, we mentioned that, obviously we mentioned things like global weather forecasting. So this was 2024, already at that time it was pretty clear that the AI driven weather revolution was going on. But something that we mentioned explicitly is that this new paradigm was not restricted to geoscience, and we mentioned explicitly AlphaFold. And about several months later, obviously, that team was awarded a Nobel Prize. I guess the practical joke is that people in Stockholm read JGR Machine Learning and Computation. So let me move on with a sort of a fairly broad and loose taxonomy of how machine learning can be used in science, and then I'm going to focus more, obviously, on space weather applications. So again, loosely speaking, we can divide the field into 2 broad areas. So one is the inference / prediction / forecast, depending how you cast the problem, which boils down to devising either surrogate models or reduced order models. Now, the word reduced order models has been used in applied math for several decades now. It has a clear connotation. Now, those also have been helped by machine learning as well. So the bottom line there, the goal in doing inference is to devise a model that runs faster than a baseline. Typically, we use physics-based model as a baseline. So there is the usual trade-off of accuracy versus speed. Obviously, an additive goal is also to possibly make accurate prediction and forecast of output of interest in the future. Something that I like to quote, it's not, again, I don't take credit for that, but I believe it's true, is that particularly in space weather, but this is true for any branch of environmental sciences, understanding is neither necessary nor sufficient for prediction, which means that if the goal really just is to make prediction, I think machine learning really excels at doing that. Then a different sort of area is data-driven discovery of either models or algorithms. And then there the goal is to either discover some new physics from data. I think this has always been, in a sense, the long-term goal of using ML in physics or in other scientific endeavors. I don't think we're getting there, I believe. I don't think any major breakthrough has happened yet. Another more maybe closer to us goal is to find new parameterization of missing physics in models. I do have an example of this kind of approach. Now, I'm not going to go through a review of all the ways the machine learning has been used in space weather. That will take several hours. I just wanted to point out, and this is kind of a random, very non-exhaustive list of works, but I just want to do a list of topics where machine learning has been used extensively in the last, I would say, 5 or 6 years. The first one, which is a topic I'm still fairly active on myself, is solar wind forecast, either in terms of background solar wind or coronal mass ejections. Radiation belt fluxes has seen a lot of activities, especially using Van Allen probes data in the last 10, 15 years. So I've been able to either nowcast or forecast fluxes, electron fluxes, particularly in the radiation belts. Solar flares, possibly among all the space weather topics, is the one that, just by counting the number of papers, possibly the one which is most active. It was mentioned already in the panel before. Obviously, what is still missing is a good coordination between all these different models and ways of benchmarkings. But we are not lacking models in this area. That's for sure. And typically, the goal there is to try to predict whether an active region will produce flares in the next time horizon of typically 24 hours. Already mentioned coronal mass ejection, the arrival time of a CME or the way it propagates, the speed and so on, whether it will impact Earth or not, obviously has a huge impact for space weather on Earth. Geonetic indices going more towards the magnetosphere. There are a number of proxies that we've been using for decades to sort of estimate or approximate the state of the magnetosphere. And there are many papers doing machine learning, essentially most of them on time series analysis of L1 data. Something even close to Earth, the ionosphere, is the neutral density estimate. This is a topic that has become more and more relevant. Again, this was mentioned already in the panel for LEO satellites and anything to do with the ionosphere. Now that we are living in an area where there's going to be a congested low Earth orbit, it's important to be able to estimate the neutral density, estimate the probability of collisions, and so on. Now, again, it was not at all, very far from being a full review, but the bottom line here is that if we look at machine learning in heliophysics in general, I would say that in the last 10 years or so, ML has been applied pretty much to any task in heliophysics and particularly in space weather forecasting. I doubt that there is a single task that where some researchers, some groups have not tried machine learning techniques with mixed results, I would say. But typically, if you look at the literature, machine learning algorithm claims to be outperforming the physics-based equivalent in terms of accuracy, computational cost, you name it. Again, the problem typically is that there's not a fixed given community-driven way of benchmarking any of these methods. So it's typically up to the burden is up to the author to show that those methods actually outperform baseline models. So you may be familiar with this bell curve, which is called it's a diffusion of innovation, where typically there is a minority of true innovators, and then there are early adopters, and then at some point the topic becomes kind of adopted by the early majority and so on. Now, I don't have, this is obviously a qualitative picture. I don't even know if it really works as a bell curve, but just looking at the numbers, again, of papers and abstracts out there, I think that the community, I mean, we are somewhere there in around 30%. So the kind of the still early majority of the community works in machine learning, but I would say that the larger majority still has not been affected so much from machine learning. Something else I want to mention, again, apologies for the self-referencing here. Okay, this is on the left was the first ever book that collected works on machine learning techniques for space weather. This came out in 2018. I guess at this point we should think about doing a second edition, kind of revised and updated, because in these last 5 years, so many new techniques have come out that it's worth updating the literature. Also, we've been doing at this point 3 editions of the Machine Learning in Heliophysics conference, which I would say has been quite successful. Obviously, we went through COVID like everybody else, but the last one we just had last September in Madrid and at the ISHA Center, and I think we had a very broad view of many topics, so I really enjoyed that. Okay, I'm gonna switch gear a little bit. I'm gonna talk about open challenges for using machine learning in space weather. Again, a bit more self-referencing here. So about, don't even remember, there was 2018, 2019, I was asked by AGU to write a review paper about using machine learning in space weather. I think that was the year when AGU had the 100-year anniversary, and they were collecting a number of papers. So this was a sort of a massive, massive job for me to write. I mean, as all review papers, this is very long and to some extent boring. It is obviously, as all review papers, especially in these active topics, mostly outdated now. But I believe it's still a good read, especially for people that are new to the field. The most interesting part of the paper, for me to write, but I believe also for the readers, is at the end I took the opportunity to sort of lay down what I thought was going to be a roadmap in terms of open challenges. And in fact, these 6 open challenges that I'm going to mention now briefly kind of dictated my own research agenda for the following year, and still do. And the reason why I want to mention this is because I believe that none of these has been solved or not solved completely, and I think it would be nice to see community effort in any of those challenges, because those are really the things that we need to overcome if we want to have a true machine learning system that does operational space weather forecasting. Okay, let me start with this short list. So the first one is what I call the information problem. In machine learning jargon, this is called the feature extraction. This is possibly the hardest problem, and as I said, I don't think we have cracked it yet. So the problem is the following, especially if we want to use remote sensing. So let me just preamble this very quickly. The majority of machine learning methods in space weather use in situ data from L1, and they work fairly well in the sense that it's fairly easy to do prediction based on L1 data. Obviously, the downside is that the lead time, once you have information from L1, boils down to less than an hour. If we want to do long lead time prediction, at this point, we need to use remote sensing like solar images. These are SDO images that were mentioned by Lika, for instance. Now, the major challenge there is that we have, again, it's an information problem. So at any given time, we have about 200 million pixels from these images. Those are high resolution images for K by 4K. And typically what we're interested into is to forecast a few scalar outputs in terms of solar wind speed, geometric indices, maybe solar indices or things like that. So there's a huge dimensionality reduction, and the noise to the signal to noise level is fairly low. So what has been done in terms of machine learning is to use the usual tools in terms of machine learning methods that have been developed for in computer vision or image recognition and so on. I don't think that those tools are very well suited or adaptable for this task. We really need to come up with kind of tailored methods for the sun, especially. The second problem is what I like to call the gray box problem. So this is on the top left is a figure that now has become fairly famous from a review paper by Karnedakis et al., where basically about physics for machine learning. So basically these are the two different regimes and sort of the sweet spot or the trade-off in between, where you can have work with lots of physics or base your intuition or your models on physics and use make little use of data, or on the other range, on the other end of the spectrum, you can in principle use no physics at all. If you have a lot of data, do a completely data-driven approach. Now, in many cases, I think it's believed that there's a sweet spot in between, like this is the idea behind physics for machine learning, where you restrict your search space, your parameter space, and your solution space being enforced or constrained by the physics we know, which is quite a lot in solar and solar terrestrial physics. Now, one example of this gray box approach that I worked on about 5 or 6 years ago is when I was working with the NOAA Space Weather Prediction Center, and at that time we were interested in enhancing the operational geospace model, which is essentially a global 3D MHD model with machine learning. And obviously the details, for the details you can look at the paper, but this one plot, I think it's too bad that I didn't capture the legend in the plot, so it's not very easy to understand, but essentially going from yellow to blue to red, you have an improvement or truth skill statistics. This was in particular for forecasting the ground electric field at a given station in Canada. And again, if I didn't forget to cut out the legend, red, yellow will be data-driven, blue will be physics-based, and red is the gray box approach, if I remember correctly. So again, red, which is the gray box, which sits in between a fully data-driven and a fully physics-based, sort of gives you the best performance of all three. Now, the surrogate problem, this is a problem, particularly in space weather, where now we tend to see space weather as a chain of different models and different physics, because it's so complex to do the so-called sun to mud modeling. And so this is where machine learning can help, kind of making a surrogate or emulator of one particular chain, one particular piece of the puzzle. something that Pratik has been working on intensively, for instance, is to do an emulator or a surrogate of a 3D MHD model. Now, this is still work in progress, but I think we have some pretty good preliminary results. Now, the end goal, if this works out, is that we will have the capability to run something as accurate as an MHD model, but with thousands or 10,000 speed up in computational cost. So as probably everybody know, running a 3D MHD model is fairly expensive. You need HPC, many cluster with many nodes, and so on. A machine learning model that will have similar capability will run much faster or with much less resources. So I'm not going to go much into the details of this, but essentially what we're going to use, we're trying to use is something called the neural operator, or more accurately, a physics-informed neural operator. So this again lives in between the data-driven and the physics. Okay, the kind of challenge number 4 is what I like to call the knowledge discovery problem. This is putting back the hat of a physicist. And at the end of the day, when I mean, it really depends on what the task is, but oftentimes, even when we train a machine learning model which is fairly accurate, the question is always, how do we distill some knowledge and improve our understanding of a given system? Or in other words, how do we open the black box and reverse engineer the machine learning algorithm? Now, this is a very active area. It's what's called explainable AI. Yeah, the literature is really rich in this area. Something I want to mention here is a way, again, of using physics-informed neural network to do a data-driven discovery. In this case, this example was for the radiation belt study. So you see the equation on the bottom here. If you take the first, so this is the equation that describes the evolution of the phase space density F. This is a simplified sort of 1D equation. So this is just a function of time and L, which is sort of the radial distance. And for the last 40 years in the literature, you will find that the standard model for this kind of physics, so the transport model for electrons in the radiation belt, has been a diffusive model. So the standard model is just basically accounting for the first term, which is diffusive, and there are ways, sort of first principle way of deriving the diffusion coefficient. Now, what we proved in this paper is that actually you can capture some missing physics by kind of stepping back from the diffusion paradigm and doing a Fokker-Planck equation in terms of advection diffusion equation, where C and D, now C is an advection coefficient and DLL is a diffusion coefficient. In this context, those can be completely learned by data. So this is an inverse problem where we have data from Van Allen probes, and you use the data to train a model that gives you the correct answer or the optimal answer for the diffusion and advection coefficients. Now, what is really interesting to me is that, I mean, there are a number of things in this work, but so after solving this inverse problem, you find the optimal coefficients, and this is completely general. There are in geophysics, I would say, solving inverse problem has been done now for decades, and typically what is done is some sort of Monte Carlo approach, and always boils down to find the right parameterization for your coefficients. Now, what I really like about PIN, physics-informed neural network, is this. I believe it's the only method that can solve a general inverse problem without using any a priori parameterization for the unknown coefficients. And then when you solve the problem, you have a complete map, like in this case, of the coefficients as a function of time and space. And then you can try to learn whatever physics you want from those coefficients. Sort of a side product of this work is that you can do automatic event identification, and this is a table that was in that paper, where basically, and I'm not going to go much into the detail of how PIN works, but essentially you have a term, a kind of a regularization term in your neural network that is a residual of a partial differential equation. And that tells you, so you can plot that sort of graphically, as we did here, as a function of time and space. And so in this case, obviously the plot is kind of saturated, but whereas yellow, those are regions in which the PDE, the underlying PDE, is not solved very well. So in other words, this is telling you when the assumption that the physics was a Fokker-Planck quasi-linear kind of equation is not matched by the data. So in other words, this is a way of finding events which are unusual or not, or don't follow the quasi-linear assumption. And then so we did this completely in an automatic way, and then we looked at the data, and for some, so this is the table here. For most of the times when this happened, there was some literature or some papers studying that particular 2 or 3 days event, explaining why that happened. Now there are some cases where we didn't find any associated papers, so this might be a good way of kind of guiding the more observational oriented people in the community to try to understand what happened in those days. Okay, let me grab again. Okay, so what I really wanted to talk, maybe I'm gonna do now in the last 20 minutes or so of the talk, are the last two challenges. One is the uncertainty problem. So this follows obviously the philosophy or the school of thought which I subscribe to, that a forecast is not a forecast if it's not probabilistic. This is still very much a problem in space weather. If you look at the literature or the model used, I think the majority of them, the output of the model still gives you like a single number without any estimate of the uncertainties, which doesn't really make it usable in any operational sense. So there's a clear need of understanding and assessing the uncertainty of those predictions. So I'm going to talk more about this accrue model in the later slides, but this is the way I particularly have approached the problem of associating uncertainties on top of deterministic models. And then the sixth one, which in recent times I've come to think that, well, it's something I've been working on recently myself. And to me, this is one of the major roadblock of using machine learning in space weather is what I like to call the too often too quiet problem, or in technical term, the imbalanced regression. This was mentioned also by Lika. If we take a large number of years of space weather data, possibly only less than 1% of the data set is interesting. Everything else is just quiet time. Nothing really happens, and it's very simple for a machine learning model to predict something during quiet time. It's really hard to predict accurately non-quiet times. So yeah, this is a preprint of a paper where I suggest an algorithm to overcome this problem. I'm gonna comment on this later on. So as Pratik mentioned, we've been doing this for a while now at the University of Colorado at Space Weather Track, and we have a number of models that are real-time or quasi-operational. Now the two kind of engines under the hood are the following. So one is accrue. Again, this is the paper on the top right, and the other is ProBoost. We don't really have a paper for ProBoost, but it's described in this DST prediction paper by Andong Hu. So I'm gonna quickly give you sort of a flavor of how these two methods work together. So accrue is a really simple model, to be honest. It stands for accurate and reliable uncertainty estimate. It tries to answer the following questions. So you have a deterministic model. It's really model agnostic in the sense that the underlying deterministic model can either be a physics-based model, can be empirical, can be machine learning, doesn't really matter. The bottom line is that it's deterministic, meaning that for any given specific set of inputs, always gives you the same output. So obviously here the plot is just for visual representation because things are never 1D. But if this was a 1D problem, so X would be your input. So f of X is the model prediction. So you have this single point prediction. So this smooth red line given by the deterministic model. Then you look at the data, and obviously you have latent variable, you have uncertainty, errors in the observation and whatnot. So you have what is called the heteroscedastic uncertainty, meaning that in some region of the data, you have larger uncertainties, and in some regions you have smaller uncertainty. So the bottom line really is that we want to have a robust method to derive those blue line, those confidence interval, which typically is a function of the input. So this is what heteroscedastic uncertainty means. Uncertainty, which is itself function of the input. So it varies with the input. So once again, how to estimate the uncertainty of the deterministic model. So the simplest setup we can think of is that given a deterministic model that produces a scalar output that we call mu, and we'll explain in a second why we call this mu, and given the true values that we, for the time being, we assume to be noiseless observation, we want to produce a probabilistic forecast in terms of Gaussian probability density. So basically, we use the output of our model as the mean value of a Gaussian distribution. So that's why we call this mu, and all that remains to be estimated is the standard deviation or the variance of the Gaussian distribution as a function of the inputs. So the question is then, how do we define the optimal variance? And so we have been very much we look basically at the literature in atmospheric or meteorological science. As Pratik mentioned, they are several years ahead of us, and this problem of doing uncertainty quantification for weather prediction has been studied for a while now. So to the very least, the two characteristics we want for a probabilistic forecast is to be accurate and reliable. Now I'm going to explain what this means. Now, for accuracy, there are a number of metrics you can use. The one we decided to use is called the continuous rank probability score, or CRPS. This is, in a sense, is a generalization of the Breyer score, or the mean absolute error, essentially, for a continuous, for a probabilistic forecast of continuous variables. The way to understand this intuitively is the following. So, okay, the formula is up here, doesn't really matter, but so if you have a forecast which is probabilistic in terms of a Gaussian, your forecast is a red line like this one. It's a Gaussian centered around a given value with a given width, right? Then you look at the observation, and the observation obviously is a single point, single value. Now you can transform. So this one on the left is the PDF, the probability density function. You can look at this plot in terms of the cumulative density function, where the PDF here, the Gaussian, becomes a sigmoid, and you can associate a step function or Heaviside function for the observation, and essentially the CRPS is a measure of the area between the two, or the area square. So intuitively, obviously, the smaller the area, the more accurate your prediction is. To the limit where, when the standard deviation gets to 0, your PDF, your Gaussian PDF becomes a delta function, and basically you're doing the deterministic prediction, and the CRPS converges to the mean absolute error. Now, reliability is a different beast. So CRPS basically is a metric that you can define for every single prediction of your model. Reliability is more of a statistical property of your model. The one way to understand this is to look at what's called the reliability diagram, where you have the predicted probability of an event on the horizontal axis and the observed frequency on the vertical axis. Now, the way to understand this is to ask a question, for instance, in the case of a binary classifier, like does it rain or does it not rain, or rather, what is the probability of rain? Now, if you take all the times that your model gives you, 40% probability of rain, and out of all of those times, it actually rains 60% of the times, it means that your model is underconfident, so you're above the diagonal line. The other way around, obviously, if you predict 60% and instead it rains only 40%, you're overconfident. So the sweet spot obviously is to be on the perfect diagonal line, and this is what is called the reliability of a model. And so in the accrue paper, basically we derived a score to estimate the reliability for those Gaussian forecasts. Now, what is really interesting is that within this setup where we use the output of the deterministic model as the mean of our model, and then we just put a Gaussian on top of it, it turns out that the reliability and accuracy are competing objectives. And this is shown in these two figures, which might not be super easy to understand at first sight, but essentially, so let's look at the one on the left. So this is again the reliability diagram. So in this case, NLPD, it's a bit of mixed up of nomenclature, sorry about that. So NLPD is another, it's like CRPS essentially. It's another way of computing accuracy, is computing the negative log probability density. So the one on the left shows that we have two different models, the blue and the red line. One obviously has almost perfect reliability, the blue one, and the red one has a not so good reliability. But I mean, those are kind of toy problems, kind of build up to make the point, but they have the same accuracy score. So NLPD is the same. The other way around, you can start with one given model, the blue one on this is the plot on the right hand side, with a given value of accuracy. Now remember, those metrics are negatively oriented, so going towards 0 means better accuracy. And you can see all the different lines, so you can play with the model artificially in such a way that the accuracy gets better and better, but the reliability gets worse and worse. So again, this is just an intuitive way to understand how these two are competing objectives. So what accrue does really is the simplest thing you could do. Again, the task is to estimate the optimal Gaussian width or the standard deviation in a way that somehow optimizes both accuracy and reliability. So this is a two objective optimization problem. We define a total AR cost, accuracy reliability cost, which is just the sum of in reality is the weighted sum of two cost function, one for accuracy and the other for reliability. Again, the bottom line is that they cannot both be minimized simultaneously. We have to find the best trade-off. There are a number of ways you can, so this is a two-objective minimization problem. You can do this in a number of ways. What we found really easy and interesting to do is to set up this as a neural network optimization, where a neural network takes the same inputs as your underlying model, the deterministic model, and then finds the minimum of the cost function. Okay, so one thing which is nice about accrue, which I like, is that unlike the majority of the methods to estimate uncertainties, this does not require running ensembles. It's really plug and play. The code, there's some code available there. Now there's a paper under review which extends the assumption of Gaussian distribution into more general distributions. And this paper here is an example where we have shown how to use these in the context of space weather. Now, the next thing I want to talk about, let me check the time, is ProBoost. As I said, this was showcased in a paper for DST prediction, and the idea is fairly simple as well. It was kind of inspired by gradient boosting, so I need to explain how gradient boosting works in just one slide, if I can do that. Gradient boosting is one of the most popular and most powerful methods in machine learning. The idea is to build a hierarchy of model. So in this case, for instance, for a regression model, you have your training data set, you build a regressor, and then you look at this is what it's supposed to be shown in the top right figure. You look at the residual, which is the error of the model with respect to the ground truth, and then you train a second model on top of it, where the target is the residual of the first model. And you can play this game a number of times, and at the end you have an additive model where you can just put together the output of each individual submodel, and this has been shown to be fairly powerful in improving the accuracy. Now the problem, of course, is that it's very much prone to overfitting, and the strongest problem of gradient boosting is that it underperforms under imbalanced data sets, which is exactly the problem we are into in space weather. So the plot on the bottom here shows a prediction for DST, the geometric index, done with gradient boosting. So the blue line is the ground truth, and the red is the prediction. And you can immediately see that the model does extremely well everywhere except during the storm. So this is really the showcase that this model, as powerful as it is not very useful in the case of imbalanced data sets. So what we've done, it's kind of a generalization of this into ProBoost stands for probabilistic boosting. So because we can use accrue to identify regions where a predictor works well and where it doesn't in terms of looking at the uncertainty, and we can do this in feature space. We can subsample the feature space in such a way that let me see if I have, we can still create an ensemble of models, or rather a hierarchy of models, where the subsampling criterion is based on the accrue uncertainty. And then once we have these different models, we can combine them, weighting them by their precision, which is the inverse of the standard deviation. So in other words, for any given value of x or the inputs, we have the uncertainty for all the different models. The models that are the largest uncertainty are weighted with a smaller weight. So this is exactly, as I was mentioning, the engine that runs behind the live DST that runs 24/7. Now, this is a bit of an old snapshot. I think if you go on the website, there's a nicer interface here. It's very much interactive. You can play with it. And there is also sort of a real-time kind of benchmarking on the bottom of the plot. It shows you exactly what are the error of the models. There are ways to compare different models, the Zwipsy model as well, and so on. Something that we've been working on is also what's called the live wire on the same website, and this is the paper associated with that, also authored by Andong. This is a forecast for geoelectric field, so the value of the electric field on the ground over the continental US. Now the paper itself worked on 1 hour lead time on, I think the paper was kind of a proof of principle on the Boulder station only, and now there's work in progress, well, pending R2O2R proposal, I should say, on extending this over a grid over the continental US. This is also an interactive map. I mean, you can play with this. You can essentially click on any given point on this grid, and on the bottom you will see the time series at that particular location. Okay, if I have 5 or 6, 10 minutes, I'm going to wrap up talking about the too often too quiet problem. So this imbalance regression, this is very much work in progress. I believe most of you are familiar with it, so I'm going to just skip over. The bottom line is that all regression targets in space weather are skewed, very much imbalanced. Taking DST, which is our usual sandbox for machine learning in space weather, this is the cumulative distribution function over several years of data, if not decades, where the interesting events, namely when DST goes below -100, are literally less than 1% of the data set. Now, I'm not going to go through the details of how Paris works, this new algorithm. I recently, I was about to say published, it's only a preprint for now. Those are the 2 typical strategies to deal with imbalance regression. And I have to say now, I've tried many different strategies that didn't seem to work very well in the space weather arena. So the 2 big families, either to resample your data set, so either oversample the rare events or undersample the frequent ones. There are some methods that do some synthetic data generation. The other strategy is to reweight your loss function, so just put some weights for different samples depending on what is their frequency. Okay, I'm not gonna show any details about this new algorithm, but basically it's pruning in the sense of subsampling. So it almost goes the other way around. So you have a large data set, most of it is non-informative for your task. You want to reduce it to the smallest possible, but still informative data set that is good for your task, in this case, DST prediction. And we use something called the representative theorem to come up with a closed form equation that tells us every time we subsample our training set, so we take away one sample from our training set, what would be the estimated change in the loss. Now, what this plot and table shows, maybe the table is easier to understand. So this is the root mean square error on the lowest percentiles on a test set for DST, meaning that, I mean, this is another message I wanted to pass over. So the root mean square error, the way it's used typically, is not very informative because it's an average over many different samples. What you want to do is a conditional root mean square error, meaning that you only look, for instance, in this case, in this table, to the 1%, the smallest 1% samples in your test set, and you want to compute the RMSE only on that subset. This is exactly what is shown as the in the figure. So basically, those are the RMSE condition on the threshold, which is shown on the horizontal axis. And now the remarkable thing here is that Paris, so those results where you can see Paris sort of outperforms other methods, including baseline and other methods, up to until 10 or 15% lower percentiles. So here Paris has been trained with only 25% of all the data set that has been used for other methods. So this really shows how, if you know how to choose a subsample of your training set well, that will actually boost your performance for imbalanced regression. Okay, I think I'm gonna skip here. So the summary is that machine learning for space weather is the quintessential field, interdisciplinary field. I kind of make a quick summary of 6 problems. I mean, obviously there are more, but this to me seems to be 6 important and challenging problems that not only hinder progress in space weather, but are fundamental challenges in general in the field of AI and uncertainty quantification. So the information problem, the gray box problem, how to derive surrogates, how to derive uncertainty, obviously the imbalance regression, so the too often too quiet, so that we have to do with rare events problem, and finally how to distill some knowledge and do some proper discovery and the explainability problem. So once again, if you have work related to machine learning and space physics or geophysics in general, look at JGR machine learning computation. This is my QMUL email address if you want to keep in touch and ask any question about any of the stuff related to machine learning and physics. I'll be happy to have a chat. Thanks a lot for the opportunity, and I'm happy to take any question.
Thanks, Enrico. It was very thorough. So let's start the discussion segment, the session. I'm seeing one question, Ketki, very generic one.
Yes, it's
Yeah,
very
Ketki, go
general
ahead.
question. I just want to ask, like, we have like wide range of neural networks that are available. So, for forecasting, how do you decide like which one to use? Because, and we can take the example of DST index. I have worked in brief with the DST index. We use convolution neural network, and we discovered that it is not the best neural network to use for forecasting DST index. Then how do you decide in such cases that which one to use for which purposes?
Yeah, it's a good question. It's one of the crux of machine learning, right? There are too many options. My advice is always to start simple, and there's the tendency to do the opposite nowadays, especially for the purpose of publishing. I would say just to take the most recent shiny tool. My approach is that you should always be able to justify your choices. So especially when the choice comes at the expense, computational expenses. So I would always start simple, like literally like MLP, and see. That always gives you the opportunity to not have a baseline, and then you can think about why and under what circumstances the network fails and what is needed to add more complexity, and then we'll give you a baseline that you can compare with. CNN, yeah, now it depends really on the problem you're talking about. I think the major problem using CNN with images, with solar images, is that by construction, CNN sort of impose a translational invariance that doesn't make any sense for solar images, right? So if you have an active region in one place respect to another place, that makes a huge difference for the for whatever forecast you're doing. So I've seen papers doing transformers on solar images. Again, I don't think there's this goes back, I guess, to the notorious no free lunch theorem in machine learning, where there's not one silver bullet for all the problems, right?
Okay, thank you so much.
Yeah, thank you.
There's a question from Ranadeep.
Yeah.
Yeah.
My question was about the extreme eruptions, like where the occurrence rate are very less. So I was wondering that how AI-based forecasting could perform for those cases. Like, can they also capture some kind of inherent scaling between the different energy scales of those eruptions and can still do good?
Yeah, I mean that's the hope, right? I don't think we have had any major breakthrough in that area, and I would almost say also for terrestrial weather forecasting, I think they're still struggling with extreme weather. That's exactly the reason why I started working on this Paris algorithm to see how well you could do into. The problem with extreme events is that they are rare, right? So you don't have a lot of those into your data set. So for me, the approach that is promising is either on one end to constrain the AI model with physics informed machine learning, on the other hand to find the optimal data set to train on. Now scaling, as you mentioned, this might fall into the realm of adding physics constraint. But another thing I want to mention is that oftentimes I think there's a bit of misunderstanding about the ability of capturing extreme events. To some extent, I don't know, maybe people that do space weather forecasting like operationally day to day, I don't know if they agree with that. But to some extent, predicting extreme events is easier than predicting sort of mid-range events, especially about timing and so on. Because the error that you put on top of extreme event, in other words, if there's a strong event with a DST that goes below minus 500, if your model predicts minus 450 instead of minus 500 or even minus 400, now if you have a plus minus 100 nanotesla error bar, it's still a very good information for the operators, right? Because you still predict a strong storm. So being very accurate for strong events is not as important as if you predict minus 150. Then obviously you don't want a plus minus 100 nanotesla, right? So I think in a sense it's easier to predict extreme events rather than, again, for people that actually do forecasting, if they see a very strong CMEs, they know that it's coming in 2 days or 3 days. The mid range is much harder to predict.
Thank you.
And there's a question from Amya. And if you have anybody has question, please raise your hand and unmute yourself. Yeah, someone.
Hi, Enrico. Thank you for the very nice talk. So I think my question sort of carries forward from the previous panel discussion, as we were discussing that although it might seem like we have a lot of data, a lot of it is not very interesting because you have a lot of quiet period. So given that, do you think that sort of limits our ability to reliably use something like a supervised learning scheme? Like, how do we ensure that whatever our models are learning is not getting sort of biased by very specific correlations in data sets, like specific types of maybe observation bias? Yeah.
Yeah, I guess it goes back again to to how to select the training set. I mean, we do know now for many years of practice with machine learning, also in other fields, the sort of correct way of estimating the generalization ability of a model, for instance, doing cross validation, leave one out, the kind of stuff. So I think we know how to decide whether a model prediction was, say, particularly lucky because it was trained on a particularly lucky training set, or whether that generalizes well. Now the problem still stands of how to, again, to me the task, the challenge in space weather is how to, so we don't need more data, we need better data in a sense, and possibly smaller data with respect to what we have. So to me, the task is how to select, how to subsample the training set so that it's the most informative for that specific task.
One question from Teja. Would you like to ask yourself by unmuting? If not, then I can just state the question. He's asking that how well AI-based forecasting on specifically something like sporadic E is possible. How challenging is it?
Yeah, it catches me a little bit. This is not particularly my field. I know there are publications about that as well. There are I mean, as I said at the beginning, you can find a publication pretty much on anything using machine learning for any physical space weather task. Now, I can't really comment on how well they do, or what. I mean, I'm pretty sure that there's always room for improvement. So I can't really help in this sense, I'm afraid.
Okay. So he has a follow-up saying that sporadic E is being a key variable in space weather forecasting, isn't it?
Not sure, to be honest.
Yeah. Okay. Anybody else? Do you have any question? I think it's quite late.
Yeah, thanks a lot for accommodating the schedule. I realize it's really late in India. I was teaching this afternoon. So.
Yeah, but it was a very thorough thing. I don't know how many people would have kind of understood the importance or relate to it, because I think majority of the audience are not ML method pro people, but mainly modeling and observations. But I think they must have got a very good taste of what are the problems that can be tackled through machine learning.
Okay.
And this uncertainty problem is quite intriguing. I think, do you think that Acure, since it's model agnostic and doesn't require ensembles, so I've been reading about the conformal prediction, which is also doing same thing, and maybe other methods might be there. I'm not aware of it. So do you see any similarity, or which can be better? Should I use this Acure?
Similarity. Yeah. That's a good question. I'm aware of at least another one. So there's conformal prediction. There's one called Easy UQ. I think the difference is whether they're working sort of parametric versus non-parametric. Now, this manuscript I mentioned, there was actually work of a CU PhD student in applied math. She has been comparing the three for non-Gaussian distributions. And obviously, I mean, I don't know how general those results are, but yeah, the accrue method seems to be competitive, if not outperforming these two. Yeah, it's definitely something worth investigating a bit more. There's also, recently I found sort of a review paper by Peter van Leuven, which is at Colorado State University. He's a data simulation person, but he has done a nice review about all different UQ methods, specifically for machine learning, including deep ensemble and whatnot. I think, I mean, it's a topic which is has been studied for a while, but it's very much open how to do a proper UQ on top of machine learning. And it's very relevant for everything operational, right? So
Yeah. And machine learning as well as MHD simulations, because they are fully deterministic. If we have some scheme which can provide some uncertainty or change the deterministic into probabilistic through a wrapper, that will be also beneficial for like computation people, not just here.
Yeah.
Okay. Last call for any comment, remark, anything from the participants. Okay. If not, then probably we will end here. Thanks, Enrico, for putting this effort and presenting this AI thing.
Yeah, thank you very much for the opportunity. Have a good rest of your evening or day. Bye-bye.
Thank you.
Thank you.
Okay. So I think I forgot to take the group photo this time, but I think we have taken for that session that can.
I have taken for the panel discussion as well, but the cameras were not on for everyone. So just in case, because
yeah. So if you guys are still there, can you please turn your video on so that we can have a screenshot of the participants of day 2?
Yeah, not everyone is
Thank
here,
you,
but
everyone.
yeah.
Yeah.
Okay.
Ketki, your video is off.
Oh, yes, sorry. We can say ISHA.
Yeah.
Thank you so much.
Thank you, Ketki. Thank you, guys. See you tomorrow.
Yeah. We can switch off the recording probably.
Oh, yes.